So then, your attention. Which means, like I said, these operators are extremely friendly creatures. I could multiply them and then create a new operator, which would be equivalent. In the sense that if I had like a d minus alpha acting on the output of d minus beta acting on y, what we have observed is this is the same as d minus beta acting on the output of d minus alpha acting on y. So, 1 alpha beta could be interchanged. 2, I can take the luxury of d squared minus alpha plus, imagining it to be a mere algebraic entity, plus alpha beta acting on y, right? This is established without ambiguity, without a doubt, right? Now what I am going to look at is a differential equation. I am going to look at a differential equation of order n. I am going to look at a differential equation of order n of a special type as follows. Nth derivative of y with respect to x plus a1 n minus 1th derivative of y with respect to x plus a2 n minus 2th derivative of y with respect to x plus an equal to an y equal to 0. I want to solve for y in terms of x, where a1 and a2 are fixed constants. a1, a2, etc. are fixed constants. I want to be able to solve this differential equation. Nth derivative of y with respect to x plus a1 n minus 1th derivative, a2 n minus 2th derivative, an into y equal to 0. I want to solve for y in terms of x. What's the order of this differential equation? What's the order of this differential equation? N. Highest order derivative is n, so the order of this differential equation is n. So if you have a differential equation of order n, in its general solution, how many arbitrary constants will feature? N arbitrary constants will feature, right? Right? In the general solution to this differential equation, in the general solution, GS is general solution to this differential equation, n arbitrary constants must appear. Right? N arbitrary constants must appear in its general solution. Now, so assuming you have bred familiarity with the operator D, I'll now take recourse to using D. That will save us some time and space while writing all of this. All right? Yes or no? So in terms of the operator D, this is like d n means differentiating n times. It's not d to power n, it's differentiating n times. But when I multiply, I can look upon this as a power. I could look upon this as d to power n. But when differentiating, it means the nth derivative. Right? Plus a1 n minus 1th derivative plus a2 n minus 2th derivative plus an. All of this acting on y equal to 0. That's the differential equation. That's the differential equation where this is my operator. This is my operator. Right? This is my operator. My operator is FD is my operator. FD is n plus a1 d to power n minus 1 plus a2 d power n minus 2 plus an. That's my operator, right? So my differential equation is FD, which is an operator function, which is an operator function, which is an operator function, isn't it? It's an operator, only several operators here. Operator function, right? Is it getting too terse for you, or are you okay? Right? Confusion hai kya? Acting on y is 0 is my differential equation. That's my differential equation. Yes or no? FD acting on y equal to 0 is my differential equation. Bolo. Now, I told you we could. So this is like a polynomial of operators. It's a polynomial of operators. And like I said, we could factorize operators. Like I factorize algebraic expressions, we could factorize operators. Yes or no? Yes or no? So when I factorize an operator, can I wipe this off? So for a moment, forget that it's an operator. For a moment, imagine FD to be just another algebraic expression in D. When you factorize, you'll imagine this to be an algebraic expression in D. Yes or no? So then, FD, if it's an algebraic expression in D, it could be factorized in terms of D. It could be factorized in terms of D. Right? So like I said, only for a minute or so, forget that it's an operator. Imagine this to be an algebraic expression. And FD, say, vanishes at D equal to alpha. FD, say, vanishes at D equal to alpha. Then D minus alpha must be a factor of FD. If FD, imagined to be an algebraic expression, vanishes at D equal to alpha, then D minus alpha must be a factor of this expression. Right? So FD can be written as some phi D into D minus alpha. Phi D into D minus alpha. Yes or no? FD can be written as some phi D into D minus alpha. Stop me the moment you think it's... No, it's an algebraic expression in D. If it vanishes at D equal to alpha, then D minus alpha must be a factor. So this must be D minus alpha into some phi D. So this is order 1, this must be order n minus 1. So that the total order is n. Yes or no? Right? Bolo. Pakka. So, my differential equation is, now for a moment, I have the luxury to break it up into factors. Phi D is one factor of FD and D minus alpha is another factor of FD. So, phi D acting, phi D, now let me go to the operator base of this. This is phi D into D minus alpha acting on Y is 0. Yes or no? That's my differential equation. Would you want to then believe that? So what am I trying to obtain? Y a function of x, which is a solution to the differential equation. I'm trying to solve this differential equation, right? Y a function of x. Yes or no? Y a function of x. Huh? Now, D minus alpha acting on Y is 0. And phi D acting on this is 0. Phi D acting on this whole thing. There is an output that this produces. If Y is a solution, then there is a solution produced to this. There is an output of this. Phi D, the operator phi D acts on this to produce an output 0. Such has to be Y. Nahin. What? So if realize that if D minus alpha acting on Y was 0, for a certain Y, if D minus alpha acting on Y is 0, then phi D acting on 0 will be 0. This will give me one possible solution to the differential equation. Yes or no? Bataएं वापस. Kichui na. What am I trying to obtain? This is like one operator, another operator, this acting on y. The output of this is being acted upon by phi d and the output produced is 0. Right? I am trying to obtain a solution to this differential equation. A solution to this differential equation. So, if for a certain y, a function of x, if the output produced by this is 0, then phi d acting on 0 will be 0. So, this equal to 0 will give me one possible solution to this differential equation. This equal to 0, this equal to 0 will give me one possible solution to the differential equation, right? If a certain y causes this to be 0, then this acting on 0 will be 0. Yes or no? Right? Now, that means d acting on y is alpha y. D acting on y is, d acting on y minus alpha y is 0. So, d acting on y must be alpha y. D acting on y minus alpha y is 0. So, d acting on y must be equal to alpha y. Yes or no? Nahin? What is d? D is d dx of y is alpha y. dy by y is alpha dx. Yes or no? Well, ki অসুবিধা হচ্ছে? You are panting for breath. Log y, one of the possibilities is alpha x. That means y is e power alpha x is certainly a solution to this differential equation. Y is e power alpha x is a solution to this differential equation. Yes or no? That means if this fd has one of the factors d minus alpha, then one of the solutions is e power alpha x. One of the solutions is e power alpha x to the differential equation. Yes or no? This of course by no means is a general solution. We are only trying to build the structure because the general solution must contain n arbitrary constants. Must contain n arbitrary constants. Yes or no? तो ये general solution नहीं है. This is one solution that I have obtained. Right? Now, if fd acting on y is 0, it's set of derivatives, right? Is it? It's a collection of derivatives. It's a collection of derivatives. Then think of a constant fd acting on y is 0. That means set of derivatives only. fd acting on the constant times y is also 0. नहीं समझ रहे है ना? If fd acting on y is 0, then fd acting on c times y will also be 0. It's like this is only derivatives, not set of derivatives. This c can come inside fd. I multiply throughout by c. This c wriggles past the derivatives and enters, gets clubbed with y, merges with y. So fd acting on cy is 0, which means what? Fd acting on y is 0, fd acting on cy is also 0. That means if y is a solution, cy is also a solution to the differential equation. That means, isn't it? If this is a solution to the differential equation, c times this will also be a solution to the differential equation. Fd acting on y is 0, it would also mean fd acting on cy is also 0. Yes or no? That means if e power alpha x, y is e power alpha x be a solution to the differential equation, then y is c e power alpha x will also be a solution where c is an arbitrary constant. Yes or no? C is an arbitrary constant. Nahin? So if there is an operator like this fd and d minus alpha is a factor of this fd, then c e power alpha x will be a solution to the differential equation. C e power alpha x will be a solution to the differential equation. Say for example, if I have say d squared minus 6d plus 8 acting on y is 0. This is my FD, which is set of operators. This is my FD for a moment. That acting on y is 0, right? I have the luxury to factorize this. So, right? D minus 4 into D minus 2 acting on y is 0. Now, if D minus alpha was a factor, C e power alpha x was a solution, isn't it? If D minus alpha was a factor, then C e power alpha x was a solution to the differential equation. Yes or no? If D minus alpha was a factor of the FD operator, then C e power alpha x was a solution to the differential equation. बहुत confusion लग रहा है क्या? नहीं ना? Clarity है ना? Right? So, if D minus 2 is a factor, then C1 e power 2x will be a solution. If D minus 4 is a factor, C2 e power 4x will be a solution. Yes or no? These are two solutions. These are two solutions. This is y1 is a solution to this differential equation. Y2 is also a solution to this differential equation. Yes or no? This is a solution to the differential equation, right? If D minus alpha is a factor, C e power 2x will be a solution. If D minus beta be a factor, C e power beta x will be a solution to the differential equation. That means I've already figured out two solutions to the differential equation. C1 e power 2x will satisfy this. Y equal to C2 e power 4x will also satisfy this. Yes or no? I have obtained two solutions where C1 and C2 are arbitrary constants. Yes or no? Now, look, if y1 be a solution to the differential equation, FD acting on y1 is 0, then I have figured out that C1, or let's say just if y1 was a solution, y1 is already in this form. If y1 is a solution to the differential equation and y2 is also a solution to the differential equation, FD is set of derivatives only. Add these two. FD acting on y1 plus y2 will be 0. That means y1 plus y2 will also be a solution. If y1 is a solution to this differential equation and if y2 be a solution to this differential equation, then add these two. FD acting on y1 plus y2 will also be 0. That means y1 plus y2 will also be a solution to the differential equation. Yes or no? If y1 is a solution to the differential equation of this, if y2 is a solution to the differential equation, then y equal to y1 plus y2 will also be a solution to this differential equation. Yes or no? So, come back to this. This is a solution to this differential equation. This is also a solution to this differential equation. That means y equal to y1 plus y2 will also be a solution to the differential equation, which is like C1 e power 2x plus C2 e power 4x will be a solution to the differential equation. What's the order of this differential equation? 2. How many arbitrary constants? 2. Very good. This is the general solution to the differential equation. Yes or no? This is the general solution to the differential equation. How about it? Got me? Confusion. All good? Huh? Now, so if I have so very brilliant. FD acting on y is 0. Imagine FD to be a polynomial in D. In general, how many roots will it have? N roots. In general, FD, if you factorize in terms of D, will have n roots. Suppose FD equal to 0. FD imagined to be just an algebraic quantity. This equal to 0 has n roots because it's of degree n. I'm imagining it to be a polynomial. So it will have n roots. It's a polynomial of degree n roots. That means FD can be factorized as n roots. Suppose, let me imagine real roots. It may not be. Suppose these are real roots Real and distinct roots. Suppose these are real and distinct roots. Suppose these are real and distinct roots. FD has real. See, in this case, these were the two roots. It was degree 2, so it will be real and distinct roots. Right? Degree in terms of the polynomial, but order in terms of the derivative. Order is 2, but imagine this to be a polynomial in D, then its degree will be 2. Clear? Which means FD can be factorized as D minus alpha 1 into D minus alpha 2 into D minus alpha 3 to D minus alpha n. Yes or no? So FD factorized as D minus alpha 1, D minus alpha 2, D minus alpha n acting on y0, where I am looking at a case where alpha 1, alpha 2, alpha n are all real and distinct, distinct. So now, alpha 1 will produce a solution C1 e power alpha 1x. Alpha 2 will produce a solution C2 e power alpha 2x. Alpha n will produce a solution Cn e power alpha nx. Yes or no? And the general solution to this differential equation would be C1 e power alpha 1x plus C2 e power alpha 2x plus Cn e power alpha nx. This will be the general solution to this differential equation. This will be the general solution to that. N arbitrary constants, as you see. Nae? Right now? I'll give me a few minutes. I'm coming to all cases. Right now I'm looking at the simplest alpha 1, alpha 2, alpha n. They are real and distinct roots of FD imagined to be a polynomial. If FD imagined to be a polynomial. Right? Right? Based on that, I factorize that, but eventually I use them as operators. Right? Acting on y0. The contribution to the solution made by this factor would be C1 e power alpha 1x. The contribution made by this would be C2 e power alpha 2x. This will be, so if y1, y2, yn are all solutions, then y1 plus y2 plus yn will also be a solution to the differential equation. Yes or no? Right? So this gives me the general solution. For example, if I had if suppose my FD was factorizable as D minus 2 into D minus 3 into D minus 4 into D minus 5 acting on y is 0. Suppose this is how I could factorize FD. Very clearly 2, 3, 4 are all real roots. So the general solution to this differential equation is going to be what? C1 e power 2x, C3 e power 4x plus C4 e power 5x. 1, 2, 3, 4. It's a differential equation of order 4 because highest derivative would be the fourth derivative. So it must have had 4 arbitrary constants. It must have had 4 arbitrary constants. Yes or no? And the interesting thing is, go back to my first session and the first few minutes that I spent in that session, where I made you go through some pain when I said there is a family of curves, say C1 e power 2x plus C2 e power 3x. Find the differential equation whose solution is this. Find the differential equation whose solution is this, where C1 and C2 were arbitrary constants. We knew that this must be a differential equation of order 2. Now, I'll say the corresponding differential equation is D minus 2, D minus 3 acting on y is 0. That's my differential equation. Yes or no? So D squared minus 5D plus 6 acting on y is 0. Or, isn't it? D2y dx2 minus 5 dy dx plus 6y is 0 is my differential equation. Whose solution is this? Right? Where it took a lot of effort to eliminate C1 and C2. We differentiated once, we differentiated twice, and got into a lot of ugly computation. Right? Now see, this works. right? And you know, now you can just play around with it. C1 e power x plus C2 e power minus 3x plus C3 e power 4x. Find the differential equation whose solution is this. D minus 1, D plus 3, D minus 4 acting on y will be 0. Multiply this out. That will be the corresponding differential equation of order 3. How easy it gets. Do you see that? Right now? Yes or no? Now, sounds good. Can I wipe this off? Suppose I had a differential, I have again an operator fd which was say d minus alpha 1. Alpha 1 is a real number. D minus alpha 2 and D minus alpha plus I beta. Alpha beta are real numbers. D plus alpha minus, I'm sorry, D minus alpha minus I beta equal to 0. Where alpha 1, alpha 2 are acting on y0, acting on y0. Alpha 1, alpha 2 are real numbers. So now this FD has 4 roots. Alpha 1, alpha 2 are roots, 2 real roots and 2 complex roots, and you know complex roots had to occur in pairs. That's why one is of the kind alpha plus I beta, the other one is of the kind alpha minus I beta. Yes or no? Right? Nahi kya? Now, let me look at the contribution made by each. Let me look at the contribution made by each. Contribution made by this is, say for example, C1 e power alpha 1x to the general solution. Contribution made by this is going to be C2 e power alpha 2x. Yes or no? Contribution made by this is C3 e power alpha plus I beta x. Contribution made by this is C4 e power alpha minus I beta x. That will be the general solution. That will be the general solution. Yes or no? Now, this is all right. I need to do some work on the last 2 terms, right? What I do is I take e power alpha x common from this, these 2. So e power alpha x taken common. C3 e power I beta x plus C4 e power minus I beta x. How about it? Just the last, these 2 terms remain preserved, right? The last 2 terms, e power alpha x taken common. So e power I beta x, C4 e power minus I beta x. Confusion hai kya beta? Nahi kya? Now, just look at these 2 terms. This is e power alpha x, C3. This is cos beta x plus I sin beta x. Right? Look at this, C4 cos beta x minus I sin beta x. Right? Yes or no? Just these, everything else remains the same. This is e power alpha x cos beta C3 plus C4 cos beta x plus IC3 minus IC4 sine beta x? Yes or no? But C3 plus C4 is some arbitrary constant P1. If you combine two arbitrary constants, you effectively get one arbitrary constant. This is P1. C3 plus C4, I choose as P1. This is one arbitrary constant. And IC3 minus IC4, I choose as some P2. P2. Yes or no? So this is like the contribution made as e power alpha x, P1 cos beta x plus P2 sine beta x. Yes or no? Essentially, how many arbitrary constants? 1, 2, 3 and 4, which is what you expected because it was order 4. Differential equation of order 4, you expected effectively 1, 2, 3 and 4, 4 arbitrary constants. Now the rule of the game is, if alpha 1 is a real, its contribution made to the general solution is C1 e power alpha 1 x. And if there is a complex solution which occurs in pair, the contribution made by these two roots, this is the combined, realize this is the combined contribution made by these two roots, alpha plus I beta and alpha minus I beta. What kind of a contribution has it made to the general solution? E power alpha x, P1 cos beta x plus P2 sine beta x is the combined contribution made by the two complex roots. Is the combined contribution made by the two complex roots. Alpha is the real part of the complex root and beta is the imaginary part of the complex root that occurred in pairs. Right? Yes or no? Say I had a differential equation which is d squared plus d plus 1 acting on y is 0. Right? Now, do you realize the discriminant of this is less than 0? So if I had to imagine this to be a polynomial, if I had to factorize this, how would I factorize this? Well, I want to factorize, it'll have two complex factors, isn't it? It'll have two complex factors. So d squared plus d plus 1, imagine it to be a polynomial in d. If I equate it to 0, then what would I get? D equal to minus 1 plus minus 1 minus 4 root 3i divided by 2, which is minus half plus minus root 3 by 2i. Yes or no? So my alpha is minus half, beta is root 3 by 2. Beta is root 3 by 2. These are the two roots, right? Isn't it? Because this could be eventually factorized as d minus half plus root 3 by 2i, d minus half minus root 3 by 2i. Yes or no? Acting on y 0. This is how it goes, right? Yes or no? I could factorize this like this, isn't it? And now my general solution, I don't have to bother about all this. Once I figured that out, I know my alpha is minus half, alpha will be minus half and beta will be root 3 by 2. So the solution to this differential equation is going to be y equal to e power alpha x. So e power minus x by 2, right, into some c1 cos beta x cos root 3 by 2x plus c2 sine beta x, right? Root 3 by sine root 3 by 2 beta x. Yes or no? That will be the general solution to this differential equation. X beta x. That will be the general solution to this differential equation. Right? क्या दोस्त परेशान हो रहे हो? कुछ नहीं बेटा. If FD had complex factors, in this case, this is FD has complex factors, alpha plus I beta, alpha plus I beta and alpha minus I beta are two complex factors ना. So roots क्या होगा? Roots उसका participation in general solution is going to be e power alpha x. See, this is what? This is the contribution made by the two complex roots, alpha plus I beta and alpha minus I beta, which occurred in pairs. What is its contribution? See, eventually e power alpha x, arbitrary constant into cos beta x plus p2 arbitrary constant into sin beta x. So in this case, alpha is minus half and beta is root 3 by 2. So what would be the solution? E power alpha x c1 cos beta x plus c2 sin beta x. That's the solution. Yes or no? Hey, the simple harmonic oscillator. And you know, if I had, in addition, if I had a d minus 1 into this was my differential, then there would be an extra term here. This would be some c3 e power x. That will be the contribution made by this. The contribution made by this would be e power alpha x c1 cos beta x plus c2 sin beta x. That's the contribution made by this. So we have looked at what happens when there were real and distinct roots. What happens when there were a set of real and distinct roots and a pair of complex roots. So every complex roots, that's the contribution made by a complex root. That's the contribution made by a complex root. Okay. Can I wipe this off? Now, differential d2y dx2 plus y equal to 0. This is a differential equation. I mean, in a simple harmonic oscillator, instead of x you had t. In a simple harmonic oscillator, acceleration in the y direction is minus k times the displacement in the y direction. This is a simple harmonic oscillation, except that instead of t I have x here, right? So this is like, do you realize this is d squared plus 1 acting on y is 0? So what the two complex roots are plus minus I of this, right? So alpha is 0 and beta is 1 in this case, isn't it? Alpha plus I beta, alpha minus I beta are the two roots. Yes or no? Alpha is 0 and beta is 1 out of comparison, right? It's 0 plus minus I. So alpha is 0 and beta is 1. Alpha plus I beta and alpha minus I beta are the two roots of this, right? So which means what would be the general solution to this? E power alpha x. So e power 0 into x, c1 cos beta x cos x plus c2 sin x. That's the solution. Yes or no? Suppose. So do you understand how complex roots are participating in the general solution? How real roots are participating in the general solution? Right? Can I wipe this off? Hey, and you know, now you could have had, say, someone could have just given you the primitive, the solution to a differential equation as e power 3x cos c1 cos 2x plus c2 sin 2x, suppose. This was the primitive, the solution to a differential equation, and they said, where c1 and c2 are arbitrary constants, and they said, find the differential equation whose solution is this. Now, very clearly, it's of the form e power alpha x c1 cos beta x plus c2 sin beta x, right? Alpha is 3 here, beta is 2. That means the operator is going to be d minus alpha plus I beta, d plus d minus alpha minus I beta acting on y will be 0. That will be the differential equation whose solution would be that, right? So now if I actually multiply this, I get d squared minus sum of the roots, right, minus this plus this, which is 2 alpha d, plus this into this will be alpha square plus beta square acting on y is 0. That's my where alpha I can replace by 3. So d squared minus 6d plus alpha square plus beta squared, 9 plus 4, 13, acting on y will be my differential equation whose solution is that, right? So d2y dx2 minus 6 dy dx plus 13y equal to 0 would be my differential equation whose solution is this. Two arbitrary constants, otherwise what would you have to do? You would have had to differentiate twice to eliminate two arbitrary constants. Now you can just go ahead and work on this premise. Yes or no? Now two cases, real and distinct roots explored, contribution of a complex root explored, right? What if FD had some coincidental roots? FD had some coincidental roots, say. Now, I will not bother you with a proof of what I am going to say, but say, can I wrap this up? How it works is, say I had a differential equation of this kind, d minus alpha whole square acting on y is 0. Alpha is a repeated root, repeated twice. So, I mean, if you say d minus alpha acting on d minus alpha acting on y is 0. Now see the problem with this. The contribution made by this is what? C1 e power alpha x. The contribution made by this is C2 e power alpha x. And now if I go ahead and say this is my general solution, then that's bullshit, because this is like C1 plus C2 e power alpha x, but C1 plus C2 is actually one arbitrary constant, which is C e power alpha x. So this cannot be the general solution, because this is a differential equation of order 2. How can it have one arbitrary constant? This is a solution, all right, but this is not the general solution, right? Isn't it? This is not the general solution to this differential equation. Now let me tell you what they do is, if you find, let's say, alpha a repeated root in FD, alpha a repeated root in FD. If alpha is a repeated root, repeated twice, say, repeated twice. This is alpha, a repeated root, repeated twice. Then, let me tell you, the general solution to this is going to be e power alpha x C1 plus C2x would be the general solution. If alpha is a root repeated twice, then its contribution to the general solution, d minus alpha whole squared, would contribute to the general solution as e power alpha x C1 plus C2x would be its contribution. If it appears thrice, if alpha is a root repeated thrice, then its contribution to the general solution is going to be, e power alpha x C1 plus C2x plus C3x squared. If I have three arbitrary constants, see, this will be of degree 3, so it must make three arbitrary constants contributed to the general solution. If I had d minus alpha to power 4 acting on y is 0, then the general solution of this would be e power alpha x c1 plus c2x plus c3x squared plus c4x cubed would be the general solution to this differential equation. That would be the contribution made by this factor. It must produce 4 arbitrary constants. In general, if I have alpha a root repeated r times, then the contribution made by this factor, would be y equal to e power alpha x c1 plus c2x plus c3x squared plus crx power r minus 1. That will be the contribution made by this. If it's a root, if it's a real root repeated r times, that's the general contribution made by a root repeated r times. It must contribute r arbitrary constants in the general solution. So if I had, say, d minus 1 whole cube into d minus 1 whole squared into d plus 2 acting on y is 0. If this was my differential equation, the general solution to this differential equation is going to be the contribution made by this factor is going to be e power alpha is 1 here, x into c1 plus c2x plus c3x squared will be the contribution made by this. It's of degree 3, it must produce 3 arbitrary constants. Now this one, I'm sorry, let me call it d plus 1 whole square. Okay. Now e power, right? E power minus x, say c1 prime plus c2 prime x would be the contribution made by this. And the contribution made by this is going to be, say, c4 e power minus 2x is the contribution made by this. Right? So if there are repeated roots, that's how they contribute to the general solution. But if there are repeated roots that are complex, or pairs of complex roots repeated, that's the last bit, deal with me, all right? But you've understood everything that I've said, right? Huh? Distinct real roots, complex roots, not repeated, and coincident real roots, repeated. Once, repeated twice, repeated thrice. We know what they contribute to the general solution of the differential equation. Clear? Suppose I had a differential equation, say d squared plus 1 whole squared acting on y is 0. D square plus 1 acting on y equal to 0 had like d plus I, d minus I acting on y is 0, and we know alpha was 0 and beta was 1, and the contribution made by this combo plus I and minus I, the contribution made was e power 0 into x into c1 cos beta x, beta is 1, isn't it? Cos beta x plus c2 sin beta x was the contribution made by this. Just one complex, one pair. They will always occur in pair. In this case, you have one pair, I and minus I. But suppose, in this case, there are two pairs. See, isn't it? D squared plus 1, acting on y is 0. 4 complex roots, 2 obtained out of this and 2 obtained out of this, and they are coincident, yes or no? The 2 obtained out of this and the 2 obtained out of this are coincident. The contribution made by this is going to be y equal to, same thing, e power 0x c1, instead of c1 you will have c1 plus c2x cos x instead of C2 you will have C3 plus C4x sin x. That will be the general, that will be the solution. If plus minus I has occurred twice, right? If I had say d minus alpha plus I beta, d minus alpha minus I beta, occurring r times, each root is occurring r times. The pair alpha plus I beta and alpha minus I beta is occurring r times. The general solution to this differential equation, the participation of these factors is going to be e power alpha x c1 plus c2x plus c3x squared plus CR x power r minus 1 cos beta x plus C1 prime plus C2 prime x plus CR prime x power r minus 1 sin beta x. That will be the general solution. E power alpha x taken common, then cos beta x would have this. These are alpha plus minus I beta, each repeated r times. Alpha plus I beta repeated r times, alpha minus r beta repeated, I beta repeated r times. That will be the contribution to the solution made if the roots were complex. Yes.